Okay. Hi, everybody. A very good evening. Right. I hope all of you are back or freshened up from your schools. Okay. Right. So we are doing amines, if everybody remembers. Right. So yesterday, if you can just recollect, maybe I can even show you. Oh, wait, I have to share the screen. Right. So we said amines are derivatives of ammonias. Depending on the number of carbon atoms attached to the nitrogen, we can call them as primary, secondary, and tertiary amines. How to name them? Right? The primary amines are just going to be called as alkanamines. If at all you have any branches, you will write those branches also, right? In terms of numbers, right? So you have to end with the where the amine is positioned, that number also have to mention, right? And you have to remember this structure and secondary amines are going to be called as N-alkyl alanine because we are going to have two carbons attached. Now, the one smaller one will be the N-alkyl and the bigger one is going to be your alkylamine, right? And in case of your tertiary, we can see that it is going to be 3. So we are going to get 2 N groups. That is N-alkyl 1 and alkyl 2, or you can write it as N-gamma and dialkyl, depending on whether it is going to be same group or different group. We have seen some examples, right? Then we talked about the boiling point. Boiling point, we're going to talk about in three different ways we can speak in terms of molecular mass, where it is directly proportional, in terms of branching, it is inversely proportional, and hydrogen bonding, if it is there, that is going to be the deciding factor for everything. And more the hydrogen bonding, more is going to be the boiling point, right? Based on that, we decided that we understood what hydrogen bonding is also. Hydrogen donor, hydrogen acceptor, what are those? Now you can understand that in R3N, in between these two, you cannot have hydrogen bonding. Right? So definitely that is going to have least boiling point among the isomeric amines. And then in case of your RNH2 and R2NH, that is a primary and secondary amine, obviously this has more hydrogen donors. That primary has more hydrogen donor. So definitely that is going to have more hydrogen bonding, so higher boiling point. That's what we wrote here also, right? And solubility, again, it's all about now ability to form hydrogen bonds with water, right? If at all the amine is dissolved in water, if it can form stronger hydrogen bond with water, then more soluble it will be, right? So based on that fact, again, we can understand that primary amines will have more solubility because more hydrogen bonds are possible. Again, in case secondary and tertiary, that also we decided order solubility in water, right? Okay. Then we went to the preparation, right? We saw two methods, and both were from alkyl halides only, right? But one was a little special, right? So first one is normal nucleophilic substitution SN2 reaction, right? So where you see that RX is there and ammonia as a nucleophile is going to attack, right? Then you see that normal united and then the H minus leaves, right? So then you'll be removing a H plus to form the amine, right? So like this reaction can continue. In the first step, ammonia was acting as a nucleophile. In the second step, what will happen is that the amine form itself will act as a nucleophile. And in the second step, again, that secondary amine form is going to act as a nucleophile. In the third step, tertiary amine is going to act as a nucleophile to form what? To form at last your quaternary ammonium salt, right? It is the NH4, that N4, R4N plus. R4N plus is what is called as your quaternary ammonium ion. And if it is an halide, you call it as quaternary ammonium halide. Right? And obviously, we saw demerits other, you get primary, secondary, tertiary, and your quaternary ammonium salt also, and that's not a good method. So then we went on to see the special one that's called Gabriel-Thalmide synthesis, right? And the specialty is that we understood that it is going to be only primary amines can be prepared, and again, only aliphatic primary amines can be prepared, aniline cannot be prepared with this method, right? We start with phthalic acid and go for the amide of the phthalic acid. This is what is your thaliamide now. This one is what is your thalimide. Right? So from that, you go for KOH you put, and then you put the RX, right? And you go for hydrolysis, you are going to go for the primary amine. The R comes from the alkyl halide and the N comes from the thalimide, right? You form this thing, and so the mechanism also. If you want, you have taken to the mechanism, well and good. If not, also it's fine, right? Okay, this is where we stopped. All right. Any questions? Anybody has? No, sir. Okay. Yeah. So moving on to other methods of preparation, right? So from other nitrogen containing compounds itself, we'll be able to produce amines. For example, say from amides, right? What are amides? How do you write the structure of amides? You have RC double bond O and N is going to be there. Whenever you have this C double bond O and N together, those are going to be called as amides. Now again, amides can be of primary amides, secondary amides, and tertiary amides. Right? Now, how do you write primary amides, for example? In primary amides, RC double bond O is there, N is there. Now, again, in case of your primary amines, what you did, now you directly go for at least 2 hydrogen atoms should be there on the nitrogen atom. Now, this becomes your primary amide. Now, in case of secondary, you will go for RC double bond O N and N. The RC double bond O and N will be an input, but here will be only one hydrogen atom. Another one is going to be another alkyl group. Right? And in case of tertiary, you will see that I will have RC double bond O, and there's not going to be any hydrogen at all. So you'll have 3, say, alkyl groups attached at all the nitrogen in the nitrogen atoms. Right? Okay. So now from this, you'll be able to produce your amides also. Right? Now, how can you produce amides? Now, that's very simple. Right? All that you have to understand is, for example, say you will be able to convert like this in general. If you have, these can be anything. This bond and this bond can be hydrogen or any other alkyl group, doesn't matter. Right? Now, what you have to understand is, if I go for reduction, this symbol always represents your reduction process. Right? If I can reduce this, all that you understand is this bond is the one which will undergo reduction. Right? Now, you will easily see that this will become RCH2. Right? And you will see that that particular N will just be there, and along with their two bonds like this. Right? So what you understand is, right, if you have a primary amide, you get a primary amine. Can we prove this? Right? Say, for example, if I take CH3CO NH2, right, and I go for reduction of this, I will be getting CH3 CH2 NH2. Is it not? This C double bond O will become CH2. That's what will happen if you go for reduction. So you're not getting a primary, you're using a primary amide here on reduction, and you're getting a primary amine. Same thing will happen for your secondary and tertiary. Secondary will give me secondary, tertiary will give me tertiary. Okay? Right? Say if at all we want to take an example, say if at all I have, not benzene ring, we'll take one. Okay, say we have C double bond O, N, CH3, and a benzene ring. For example, like this you have. Okay, now all that I have to do is, if I go for reduction, the only thing that will change is that this C double bond O is going to become CH2. So you will put this will become CH2. Then we have a nitrogen with a methyl group, and this will just stay like that. That's it. Reduction was what will happen. Okay.
Sir.
Right. Very, very simple. Yeah. Tell me.
Sir, in the reduction symbol, is that an H inside the square bracket?
Yeah. H in the square bracket. Yes, absolutely.
Okay, sir.
Okay. Right. So now we just say reduction, but what exactly is going to be the reducing agent? We didn't see yet. Right. So what are now the reducing agents you can use? Right. The reducing agents which you can use are, say you can go for SN bar HCl, that is metal in the presence of HCl, or you can go for H2 in the presence of nickel, right? Or you can go for a strong oxidizing agent like LiLH4, right? So any of these things can be used. Okay, right? SN bar HCl or H2 bar nickel or LiLH4 can be used in the place of where we wrote this symbol, reduction symbol. These reagents can come. Right? Very, very simple. Right? This is another method. Okay. Right. Now, suddenly, what will they ask you is, in the conversions, right? They'll ask you to convert, right? Propanamide to ethanamine. Right? What happens? Propanamide to ethanamine. Right? Now you're seeing here I'm going to have 3 carbon atoms, but in this one I'm going to have only 1 carbon atom. Right? So now if you go to this particular reaction where you have converted an amide into an amine by just reduction, the number of carbon atoms will not change. Right? Okay. But if they'll ask you questions like this, that means there's definitely going to be some other reaction which you don't know. And in that reaction, if you convert an amide to an amine, there is going to be loss of one carbon atom, right? And that one is again going to be a very famous name reaction, and that is going to be very, very important in these kind of conversions. The moment you see that the number of carbon atoms are reducing, say this is one of the reactions which you should come to your mind. This is, okay, what is the reaction name? It's going to be called as Hoffman bromamide reaction, or it is also called as Hoffman degradation reaction, right? It's called as Hoffman bromide reaction, or it is called as Hoffman degradation reaction. Both things means the same thing. Okay, right. Now degradation, we can understand why degradation, because the number of carbon atom is decreasing, right? Bromamide, why it comes because somewhere in the mechanism I'm going to find something called as a bromamide, right? We'll explain everything what is going to happen, right? Okay. So now what happens here, right? What happens here? Now again, one more thing is this particular thing will be used only for primary. That is primary amide to a primary amine. You can do this with loss of one carbon atom. Okay, this you can do, but not for secondary, not for tertiary. Okay, fine. So now let us see what exactly happens. So if you have R C double bond O NH2, this is what is your amide, right? Now I want to convert it into something like this. R NH2, and you see that this carbon atom which is there, which is the carbonyl carbon C double bond O, is not there here. Okay, and what is the reagent you will use here? Well, that is how the one carbon atom is lost. And what is the reagent you'll use here is Br2 in the presence of KOH. This is the reagent you will use, right? Bromine, that is Br2, and your KOH, right? Sometimes they can give the reaction like this. They can give it as Br2 in the presence of NaOH. That is also okay instead of KOH. Or sometimes they can give you in terms of okay, they can give it as NaOBr, because when Br2 and NaOH react, this is the compound which is getting formed. Okay, NaOBr. Same way KOH would have formed KOBr. That also is okay. So different ways, the same thing reaction will be, but eventually one carbon atom less in the amide will be forming in your amine. For example, if I start with, say, I have a 5-membered ring with a C double bond O, NH2, right? Now, if I go for this Br2 in the presence of KOH, if I ask you what is going to happen, you will write this C double bond O is going to be gone. Okay, so all you have to do is just remove this and attach this carbon atom with this nitrogen atom. That's it. So you will write NH2 directly in the ring, right? So now you can ask me, sir, where this is C double bond to go? Where this carbon goes, right? Now what you'll understand is it is going to go out as, say for example, if you use KOH, it is going to go out as K2CO3, carbonate ion. Okay, it is going to go out as K2CO3, right? So do you want to understand the mechanism of this? Do you want to know?
Yes, sir.
Okay, but that is not going to be there in the syllabus, right? But a very interesting mechanism, right? How is it that you're able to remove one carbon atom? Fascinating. Okay, fine. We'll see how it works. Okay, so first one is that, say you have this RCONH2 with us, right? Now this KOH which we write here is going to act as a base. OH minus is going to come out. Now, generally in organic chemistry, base is not something which will be donating OH minus. That generally in organic chemistry will not consider as a base. What can be considered as a base is whichever is able to abstract H plus. I take up H plus along with it. Then those kind of things when you will call it as a base. Okay. So now this is going to take out H plus from this molecule. Right. Okay. So now which hydrogen can come out? Now, if you understand, I don't know whether you know this. How do you decide something whether it can act and that can come out or not? Right? We can understand it with the help of something called as a conjugate base concept. If the conjugate base formed is stable, then we can ensure that H plus can come out. What do we mean by conjugate base, people? I have an acid. So what do you mean by conjugate base of an acid?
So when it gives out H plus electrons, it becomes a conjugate base.
Yeah. So basically, after from the acid, I remove the H plus out, right? And whatever is remaining after removing the H plus is what is called as your conjugate base. For example, in HCl molecule, from the I remove H plus. HCl is the acid, right? From the acid, I remove H plus. What is remaining now? Cl minus. Cl minus is going to be called as conjugate base of the acid HCl. Right? Same way here. Now, what I'm trying to say, after removing H plus, you form the conjugate base, right? If the conjugate base formed is stable, then that H plus can come out. That's what you understand, right? So from this, for example, if from this molecule, say I remove a H plus, minus H plus, right? Obviously, from this nitrogen only it can go, right? Now you will have NH, right? Since I have removed a H plus, nitrogen is going to have a positive negative charge in form of lone. Okay. Now you see, this is the conjugate base form after removing H plus, right? Now you see that somehow if I can say that this is going to be stable, then definitely that H plus can come out, right? So how can you say this? I'm obviously saying that resonance can happen here. This bond will come here and this bond will break. I will be able to write the resonance structure as CO minus because this bond is broken given to oxygen. And this nitrogen is now going to lose its negative charge. Now it is going to form a double bond with this carbon, right? Now you see that this negative is getting stabilized with the help of resonance. So definitely, since it is getting stabilized by resonance, this H plus which we removed is okay to remove. That's what you understand. Like this concept will absolutely work for your carboxylic acid chapter. This is exactly how you do it. Acidic strengths basics. Acidic strengths you have studied right in carboxylic acids. Use this concept. Absolutely purely you will get. Like this, after removing H plus, check whether that CO minus is stable or not, that particular conjugate is stable or not, and more the stability, more and more is the acidic strength. Okay, anyways, so that means that definitely H plus can come out, right? So what is going to happen is RCO NH minus is going to be there. This is stabilized, right? This can form, right? Now what happens? Now your Br2 molecule is there. Br is there. Now this will go on attack here, and this will go on. This Br minus goes out. Right, this negative attacks Br, forms a bond between nitrogen and bromine, and this Br minus goes out. Right? So then what can happen? Then we can write that I have R, C double bond O, N. Now one more hydrogen atom is there, and there is Br here. Okay. Right. Now you see that there is one more hydrogen atom which is here. That also can be removed. That is also acidic. Again, same concept I'll be able to explain. Negative charge will be there and again resonance will happen, right? So another base molecule will come that is going to take up this hydrogen, right? So in that process, we will form RCO double bond N. Br is already there and now nitrogen has a negative charge, right? Now again, what happens? Next year, Br2 molecule comes. Br comes. Again, the same step. This will attack. This bond will break. Right. So then you will see that I'll form R, C double bond O, N, Br, and Br. Right. So this compound which you're forming here is what is called as your bromamide. Bromamide. Right. This is an amide, but bromine is attached to nitrogen. So it's called as bromamide. Okay. Right. Now this compound will be formed. Next thing is this Br comes, and then what happens? 1 second. So this R will go here. Okay, I don't think this step I need to do. Now what I can understand is this bond, there is a lone pair. This bond, this comes here, makes a bond, and this I will not touch. This comes and attaches here, and this bond breaks out. Yes. Okay. So anyways, the bromide is still there. Right now, this NBr, whatever is there, this becomes your bromamide. Okay. Now what you're seeing is that, again, I'll repeat everything from first. Okay. This is a complicated rearrangement is going to happen. If you understand, it's okay. If you don't understand also, it's okay. Okay. I'm sorry. Why am I putting an arrow mark? Okay. And Br minus is going to be there. Understood how it is getting formed? I hope, right? So that will take up the H minus. This hydrogen is there. Still one more hydrogen. Then take up the base will take up the H plus and negative charge is there. Right. Now what happens is this strange thing happens. This lone pair will come make a bond here. This C double bond is going to be untouched, but this alkyl group is there, right? That alkyl group is going to break its bond like this. That is going to have a negative charge, and that comes and attacks your what is that? Your nitrogen atom, and this Br minus leaves. Okay, I don't know whether you're able to follow the arrow shootings. Somehow, if you understood the arrow shootings, you will see that you will form R, N, double bond, C, double bond, O. Again, we'll see the arrow shooting, how it's happening. Okay, so you start from here. This comes here. That's a double bond between carbon and nitrogen. Okay, there's a double bond in carbon and nitrogen. Okay, and this bond is broken because this bond is getting formed. This bond is getting formed. This bond is now getting broken, and that bond is broken like this. So R minus will be there, right? And that R minus will come and attack this one, that is the nitrogen, right? And then in that process, the Br minus leaves, right? So this R is going to be attached with the nitrogen. So this R is attached with the nitrogen. N and C are having double bond. N and C are having double bond, and then you see C double bond is intact. C double bond is intact. Okay. This is the rearrangement reaction. Okay, there are a lot of rearrangement reactions with this. Okay, so anyways, this intermediate is what is called as your isocyanate. Okay, and this isocyanate, obviously, you have to go for hydrolysis of this H2O in the presence of H plus. You add water to this, right? Now, what you understand is that you will easily understand if I just go here, I will write, or you just break the double. Okay, you just write, what is that? H2 and O. That's it. Right? You are going to add water molecule, right? Okay. You break this double bond, and this side you write H2 and this side you write O. So now what will you get? You will get R, N, H2. This H2 goes to the nitrogen atom. And this carbon you see is that it is going to be in the form of carbon dioxide. C double bond to this side, C double bond to this side. Okay. So at last what you end up with is your amine. This reaction happens, sir, right? Yeah.
Sir, in this step, we are adding a water molecule. So
yes,
it's follow Markovnikov's rule, right?
No, the Markovnikov's rule is where I have between C double bond C's. Here the double bond is breaking. What double bond is breaking? You see, N double bond C is breaking. So here on our Markovnikov's rule doesn't work.
Okay.
Are you able to understand?
Yes, sir.
Right. Okay.
Sir?
Yes.
Sir, but in the starting which reaction you gave, in that the product is K2CO3, right? But over here we are getting CO.
That's a very good question, right? So now you see that this is an acidic oxide, right? CO2 is an acidic oxide. Yes, everybody agrees? No, yes. No, you don't know.
Yes, sir.
Okay, now, okay, how do I prove that this CO2 is an acidic oxide? The moment now CO2 is going to get released, right? And there is water as a medium. So you will form H2CO3. Okay. And this H2CO3 will react with a base which is already there in the form of KOH to form K2CO3 plus H2O is going to get formed. That is how it happens. Okay. Right. So that is all about how your RNH2 is produced. Now you understood how the reaction works, how the mechanism works. You understood with an example also what happens. Very, very simple, right? The beauty is that you will form only primary amines but with a lesser number, one lesser carbon atom. That's it. Okay. But if you just go for normal reduction, the same number of carbon atoms, you'll be able to convert an amide into an amine with the help of these reagents, SN bar HCl, H2 bar nickel, LiL, H4, all these stuff. All right. Okay. So that is about your Hoffman degradation. So this is about from amines. Sorry, amides. From amides, how do you convert it? Right? Now again, there are still more other nitrogen containing compounds from which you'll be able to reduce. And one of the most important ones is from nitro groups, from nitro alkanes, we call them. Okay, right. Now, how do you represent this nitro alkanes? Is RNO2. This nitro NO2 group is what is called as your nitro group. Okay. Now, again, it's very simple to understand that if I go for reduction of this, wherever there is oxygen, put the hydrogens, right? So you'll form RNH2. As simple as that. Okay. So, for example, if I want to have, say, NO2 here, like this. Now, if I go for reduction, what will you form is undine, right? This is nitrobenzene, we call it. Nitrobenzene, right? And this is going to be called as aniline, okay? Right, like this, very simple. Wherever there's NO2, if you go for reduction, that part will become NH2. Very, very simple. Right. Now, again, what are the reducing agents you can use? Reducing agents you can use, same as in the case of reduction, in the case of amides, you can use SN bar HCl, right? Or you can go for LiAlH4, right? Or you can go for H2 bar nickel, right? All of these are the common reducing agents you can use for this conversion, right? Nitroalkanes to amines, primary amines. Again, only primary amines can be put. Right? Okay. Fine. What is the time? Okay, we have still half. Just give me 2 minutes. I'll be back. Okay. Right. So this also we understood, right? Nitroalkanes too. Amines also we understood. Any other ways of preparing amines I left? Yes. Another nitrogen containing compound is from cyanides. Or cyanides are also called as nitrites. Okay. So now what is the functional group then? Can someone tell me cyanides and nitrites? What is the functional group?
CN.
CN, right? So here you can represent it as RCN. Right. Now, actually, you can also take this also along with this. Isocyanides. Or they are also called as isonitrites. We'll see what are these isonitrites and isocyanides. First of all, cyanides is this. That's okay. Right? RCN. Right? Now, you can easily understand, right? If I go for, say, for example, H2 bar nickel, what will happen? This double bond will break, this pi bond will break, then both the things will get added up to hydrogen, right? So I can easily see that you will be able to form RCH2NH2. Very simple, right? Just add hydrogen across the 2 double bonds, 2 pi bonds. You'll be able to form the primary amine. Again, only primary amine can be formed if I use cyanides, right? If I use cyanides, only primary amine can be formed because this is the only way you can add the hydrogens. There is no other way, right? So if at all I want to take an example, say I have CH, no, it doesn't matter. Say I go for benzene ring with C triple bond N. Then if I go for H2 bar nickel, then what will I get? I'll get benzene ring with CH2 NH2. That's it. Okay. Right. So now, but if I take isocyanides, right? Now, how do you represent them? Is like this: R and C. This is how you represent. Now the alkyl group is attached with nitrogen. Okay. Now, if I go for H2 bar nickel, you will see that you will form RNHCH3. This is how it will be formed, right? So this will be common in the N and CH3 coming after the hydrogenation reaction is always common for isocyanates. This R might vary depending on what is the isocyanate used, right? But this NCH3 is going to be common. So what are you seeing? You're always going to get only secondary amines if I go for what? Isocyanates hydrogenation. But if I go for cyanides, I still get only primary.
Sir, I have
right? Say if I take the same, 1 second, I'll answer your doubts. Say for example, if you have this one and then you go for your H2 bar nickel, you will get benzene ring with NH like this side and CH3. This is what you will get. Okay. Yes. What was the doubt?
Sir, in isocyanate, like how is the valency of carbon satisfied?
Okay, that's a good question. Again, you have to go for chemical bonding for that. Okay, so now you have say R, nitrogen is there. Now, if at all you understand that already out of the 5 valence electrons of nitrogen, right? Now one is involved in bonding here in this bond, right? So now you see that say it will have 4 more electrons, right? So let me put all the 4 electrons like this and say carbon is there. Carbon is having 4 valence electrons. Okay, right. Say nitrogen, already it has 1, 2, 3, 4, 5, 6, right? Now already total 5. Now one more bond is coming in the form of this R. So already it has 6 electrons. So nitrogen requires only 2 more electrons to satisfy its octet, right? So what will nitrogen do is that it will take carbon's 2 electrons like this and it will get octet satisfied, right? But now carbon gave only, nitrogen took 2 electrons, right? So carbon can take only 2 electrons then. Right? That is whatever is given, that's what is taken. Right? So carbon will take again the 2 electrons of nitrogen. So now you see for each electron pair, what is that? 1 bond will come. So you can write R, N, double bond, C, but the problem is still there. It's not over yet. Nitrogen is fully over, right? It's octet satisfied. But carbon, you see, even after the bonding, it had before the dead 4 electrons. Now 2 more electrons are coming from nitrogen. It has only 6 electrons. Right? So what is going to happen now? You will see that there is still a lone pair on the nitrogen atom, which is not involved in bonding. Right? Now that is going to be given to carbon, not given to carbon exactly. It is going to be in the form of a coordinate bond. I don't know whether you have known this before. Right? Let me draw this properly. 1 coordinate bond, 2 normal covalent bonds. Right? Now the arrow mark says that the lone pair is getting donated from nitrogen to carbon, right? Now it's very simple. Again, here also 2 electrons are there. Every covalent bond, 2 electrons are required, but the speciality is that both the electrons are going to come from one of the species in a coordinate bond, whereas in a covalent bond, 1 electron from one and another electron from another one. That's how normal covalent bond. This is a special one. This is how carbon's valency is satisfied.
Yes, sir.
Okay, right. Okay, so we saw about how cyanides work, how isocyanates works. Okay, anything else which I missed for preparation? Yeah, I think that's it. Right? These are the reactions by which you'll be able to prepare your amines. Right? Next, what we'll do is we'll go for the chemical properties. Right? How and all can react.
Sir.
Yeah.
Sir, what about the isonitriles and nitriles?
Isonitriles. Okay, that's this thing. Okay. So now, if you want to write nitrite, this thing, what is that? Nitrites, right? That's what is called as your nitroalkanes. Right? Now they are okay. Right? Now you also have this RONO. Okay. So these are what are called as isonitroalkanes, or it's called isonitrites. We call it isonitroalkanes. Right now, if you try to understand, even if you reduce this, right now you see that you cannot produce amines. That is all you have to understand, right? Because the alkyl group is now attached to what? It is attached to oxygen now, right? So you will not be able to produce your what is that? Amines, but some kind of oxygen-containing organic compound only will somehow produce. Right, that is enough for this chapter. Okay. Right. So that is about this. Okay. Now chemical properties. Right. Now first and foremost thing. Right. Now tell me, ammonia is there. Right. Now ammonia has a lone pair. Right. Now the question is, can ammonia act as a base? Can ammonia act as a base?
Yes, sir.
Okay. How?
Donate lone pair.
So if a particular species is able to donate a lone pair, they are called bases, but any specific type of base they are?
Sir, if they gain one hydrogen atom, they'll become NH4 plus then. So
okay, so that is another way of
since they're
seeing.
gaining like hydrogen
H
atom,
plus.
they are acting as base pair.
So that till now only we got two different ways of explaining how NH3 is a base. One, someone said, sir, it can donate the lone pair, so it is a base. Another guy said it is able to accept H plus, so it is a base. Both are right. Right? Actually, both are two famous theories of how you explain what a base is. One is what is called as your Lowry-Bronsted theory. The other one is what is called as?
Bronsted.
That is the Lowry-Bronsted. That's one. Next one is?
Lewis acid.
Lewis theory. Right? So what does Lowry-Bronsted theory says? Lowry-Bronsted theory says whichever is able to donate a proton is an acid and whichever is able to accept a proton is a base. Now, what do you mean by a proton if you try to imagine, right? Hydrogen has one electron, right? Atomic number 1, right? So from that, if I remove an electron, I form H plus, right? Correct. Now in hydrogen, I had one electron, one proton, correct? In hydrogen, before removing the electron, I had one electron and one proton. Now in your H plus, we have removed the electron. So what is remaining there? Only one proton is remaining. Right. So when I say accepting or donating proton, indirectly I'm talking about donating or accepting H plus ion in case of Lowry-Bronsted theory. Right. So whichever is able to accept H plus will be called as a base. Right. And whichever is able to donate a H plus obviously is going to be called as an acid. That is your Lowry-Bronsted theory. Second one is what is your Lewis theory. Okay. Lewis theory says whichever is able to donate a lone pair. I should have a lone pair first and I should be able to donate it. If I can donate it, I am going to be called as a Lewis base, right? And same way, whichever can accept lone pairs, the opposite, right, are going to be called as Lewis acids. Okay, so now you understand either way. So you see a lone pair that can be donated to some other species and it also can have accept H plus to form NH4 plus. So definitely ammonia is a base. Okay, right. Now, is there anything stopping your RNH2 or your RNHR or your R3N, which are derivatives of ammonia? Everything is going to contain this lone pair, right? What is stopping them from reacting as a base? Nothing is stopping them, right? Everything contains the lone pair. Everything will be able to accept H plus. So everything can act as a base. Okay, right. So that means the first chemical property is that we are going to see that amines are basic in nature, right? Now that fact we have proved that the amines are indeed basic in nature, right? But what is going to be more fun is that if I give you different amines, which is going to be stronger base, is going to be weaker base, that we can predict, right? Okay. Now we are going to see this important term. From this questions are for short question is going to come from this area in any of the exams which you're going to write. Okay. So that is your basic strength of amines. How strong my amines are and how do I compare it? Okay, right. Now basic strength of amines there is, okay. Now you have to be careful, right? Now if they can ask two ways. They can ask you to, they can give you some amines, different amines, and they can ask you to find their basic strength in their gaseous phase or in the aqueous phase. Okay, gaseous phase means when they are gases. Aqueous phase means when the amine is dissolved in water. Okay, right. Now, what you have to understand is if they mention gaseous phase, you'll take gaseous phase. If they mention aqueous phase, you'll take aqueous phase. But what if they don't mention anything? They just give you the amines and ask you to find their orders. In that kind, by default, you will go for gaseous phase. Okay, if nothing is given, you will assume that they're asking about gaseous phase. Okay, fine. Now, what is going to be the criteria? Okay, so first we'll talk about what happens in gaseous phase, then we'll move on to what happens in aqueous phase. Okay, now in gaseous phase, what you have to understand is it is all about donation of lone pair, is it not? Because a Lewis base is something which will be able to donate a lone pair. Okay, so can I say lone pair donating ability, right? How much ability it has to donate the lone pair? Can I say it's directly proportional to the strength of the base, the basic strength, right? How easily or how much, how much donation can happen from the lone pair, right? More and more is going to be the basic strength, right? Okay, now that is one thing we can easily logically understand. Now, second thing is that if I want to donate the lone pair, and that is how it's going to the basic strength. Now I can say also this, right? The lone pair donating ability is directly proportional to availability of lone pair. That means more and more the lone pair is available on the nitrogen atom, more and more will it the ability to donate it. And obviously more and more is going to be the basic strength. Right? So now all that you have to understand is for the comparing this particular point. Right? More and more is the availability of lone pair, more and more is going to be the basic strength of the amines. Very, very important point for you to solve any kind of question. Okay, or more and more is the availability of lone pair, more and more is going to be the basic strength. What is the time? Okay, we have time. Right? Now, what do we understand from this? We'll take an example and do this. Okay, say I have ammonia molecule, NH3, which is having a lone pair. We have, say, primary amine, which is like this. Let us take maybe a specific example itself. Let us take it as CH3. Okay, this is your primary amine, right? Next, say CH3N, CH3. We have a lone pair again, right? And then we have CH3, N, lone pair is there, and one more CH3 is also there. This is your tertiary amine. This is secondary, and this becomes tertiary amine. And ammonia is also there. Everything contains the lone pair, right? Now, what did we say? We say that more and more is the lone pair available. In all of them having nitrogen atom, in whichever nitrogen atom the lone pair is most available, that particular molecule becomes the strongest base, right? Okay. Now, what we try to understand is we have to speak in terms of an inductive effect, right? Now, this point you must have been studying from your lower classes. What is that point? All alkyl groups. All alkyl groups are electron donating in nature. Is it not? All alkyl groups are donating in nature means they'll all give me plus I effect. Right? They will increase the electron density in the next atom, whichever where they are next to. Right? This will be that's what I understand. Right? In nitrogen, what you understand is only hydrogens are there. Okay. Now, in your primary amine, what are you seeing? There are two hydrogen atoms, but you see that there is an alkyl group like the CH3. So, which will try to donate more electrons to the nitrogen. So, can I say the availability of lone pair on the nitrogen increases compared to ammonia? Right? Because of the electron donating nature of the alkyl group present, that is CH3, the electron density is going to be more towards nitrogen. That means what? Electron density of the nitrogen increases. So, availability of lone pair increases. Right? So definitely compared to ammonia, availability of lone pair and primary amine is more. So this is going to be a little stronger base than what ammonia is, for sure. Okay. Applying the same logic to the secondary and tertiary amines, what do you understand? Now you see that there are two alkyl groups. There was only one alkyl group last time. Two alkyl groups and both are donating electron to nitrogen. So can I say here double time increase will happen compared to a last time? Right? And same way here, can I say there are three electron donating groups like this, right? And you see that the lone pair availability will increase thrice the amount than what it was there in case of your primary amines, right? Okay, so what can I conclude now? Can I say tertiary amines will have the maximum availability of lone pair, right? And the minimum availability of lone pair will be there for your ammonia molecule. So now I can say that the order of basic strength is like this. That means the primary amines are going to be more basic than ammonia. Secondary amine is going to be again more basic than primary. And the most basic of them all is going to be your tertiary, because that is having maximum availability of lone pair, and that is going to be the strongest base. Okay, right. So in general, we can always say this, but what if I give CH3, CH2, NH, CH3. And okay, if I give you these three compounds to you, right, then how do you decide? That is, now you see all are secondary amines, right? All of them, all the nitrogen atoms are NH and attached to other carbon atoms, right? All of them are secondary. If at all same these things are there, primary, secondary, tertiary are there, definitely we can know now what to do. Tertiary amines will be more basic than secondary, and secondary will be more basic than primary. That we know, right? But in this case, you see that all of them are primary, all of them are secondary amines, right? Now, in that case, what you have to understand is the size of the alkyl group is directly proportional to the plus psi effect. That is, more is the size of the R, more electron donating power it is going to have, right? So now, if you try to understand this point, now you will be able to answer this question, right? Now you see that here there are 2 and 2, right? So this is going to give me a very big increase in lone pair, that to twice, right? Now in this case, you see that there are smaller ones. So the lone pair availability is going to increase twice, but only a smaller increase, right? Now in this case, what happens? Lone pair is there, this side small, but this side very big. So overall, one very big and one very small, right? So what can you conclude now? Definitely the first rank goes to this, right? Double big increases, right? And second rank goes to this, and the least basic of them all is going to be this. Okay, right. So now let us make it a little more interesting. Now, if I tell that I have CH3, NH2, right? And we have this one. Yeah, tell me.
Sir, before this, I have a doubt similar to this concept. Sir, if you are telling like presence of electron donating group increases the availability of electron in that region, sir, then why are we telling like in phenol, we are electron withdrawing, electron donating group will reduce the acidic strength?
Okay. Now here the different concept is very different. First of all, here we're talking about the basic strength, right? In phenols, we'll be talking about the acidic strength, not the basic strength of phenols, right? Now that if you want to do, all you have to understand is that, say, this is your phenol, which is having your lone, what is that? So this is your OH. Okay, this is your phenol with me. Okay. Now you understand that what I told you. How can you decide about the acidic strength? Always remember this. Acidic strength is directly proportional to the stability of the conjugate base. Okay. So we already spoke about this also when we spoke about why the H plus can come out from the NH.
Yes, sir.
Right, acidic strength is directly proportional to the stability of the conjugate base. That means what? First thing, whenever they ask about acidic strength, the first thing you will do is you will remove the hydrogen atom and make the negative charge, make the conjugate base first, right? Then you can speak about the acidic strengths. And if you find that this is going to be stable, this particular anion is going to be stable, then that is going to be a good acid, and more is going to be stability, more and more is going to be the basic acidic strength, right? So let us compare this with, I don't know, with your phenol was there, and I don't know, with your nitro group, NO2. Okay, right. Do we have time? Okay, we have time. Let us compare it with OH with NO2. And here I'm taking OH with CH3. Okay, right? So I'm going to take phenol. This is OH with NO2 here, and OH with meta position, and OH with CH3 in the ortho position. Okay, right? Now again, I ask you to compare their acidic strength. This is what I'm asking, right? So now what will you do is that again, the first step will be to remove the H plus and make the conjugate base and check for their stabilities. Out of these, whichever is going to be more stable, that is going to be maximum acidic, right? Okay. Now, all you have to understand is that this negative charge is there. Less and less is going to be the negative charge, or more and more stabilized. This negative charge is going to get stabilized in the form of resonance. More and more is going to be the stability of this particular anion. Is it not? In general itself, you understand that this particular thing, if I draw it like this, right, there'll be lone pair on oxygen. This will come here. This will come here. Everything will keep on breaking. Okay, so it is already resonance stabilized. That's why phenols are good acids. The moment H plus removes, even though nothing is there, phenols are good acids. Even compared to your alcohols, alcohol resonance will happen even if you remove the H plus. But in phenols, it will happen, right? So fine, right? Everything is going to have that, but the only difference is going to be in the form of the groups attached. Right? Now, NO2 is what kind of group first? NO2 is going to give me electron withdrawing group it is. Right? NO2 is going to be an electron withdrawing group. Right? Now, that too, if there is negative, okay, let me explain you with the help of okay, this is the phenoxide ion and this is there, right? Okay. Now you see that this lone pair is there. This lone pair can come here, make a double bond. Now this double bond shifts to this nitrogen and this bond breaks. This is how you draw the resonance structure. Okay. So you will be able to write it as double bond O will be there. And this now becomes a double bond between your nitrogen and carbon. And there is one negative charge on the oxygen atom because the bond is broken. And this coordinate bond stays as this coordinate bond. Another, this one and this one are staying as such. Okay. So now what I understanding is that if you look at the phenoxides ions resonance structures, what will be the first step? This will come here, this will break. So now you will write double bond O. Now this bond is broken, a negative charge is there, and this stays and this stays. What will be the next step? This bond will come here and this bond will break, right? So now you will have double bond O, a bond formed here, a negative charge formed here, and the bond is here. Again, 2 electrons are there. This bond, this will again shift, make a bond, and this will go back, right? So we will be able to write it as negative charge here, and there is a double bond formed. Already there is one double bond, and there is no double bond O. So the last step is that you will write this, and this bond will go back to oxygen, right? So now the last one is going to be again O minus only, but now the double bonds are shifted. These are all the resonance structure of the phenoxide ion if you check. Okay. Now, if you try to observe very carefully, you are forming negative charges where and all you see. Here, here, and here. Okay. So can I conclude that the negative charge is formed only in ortho and para positions? Is it not? For the phenoxide ion, the negative charge is formed only at ortho and para positions, right? So now, if I can place an electron with the drawing group like NO2 in that particular position, see what is happening. This also will happen along with whatever we have written here, the resonance structure. Along with that, this also it can happen. But more resonance structures are coming because of this NO2 presence also. This bond will shift, that bond breaks. You are able to get this one. Right? So electron withdrawing groups is not only about electron withdrawing groups. Electron withdrawing groups at ortho positions and para positions are going to stabilize them in the form of resonance. Right? That's the reason why they're going to be highly stable, and that's why that particular acid is going to be a very strong acid. Okay? Right. So what we understand is that compared to phenol, this is your phenol, and comparing this, here this has more resonance structures, the negative is getting more stabilized. So definitely compared to this, this is going to be a better acid for sure. Okay. Now let us go to the other one. Now what is happening here? Now you see that NO2 is going to be the meta position, right? Negative charge will be formed in ortho and para, but a nitrogen is there, then it is being stabilized. But here you see that nitrogen has no role to play with respect to resonance, right? This NO2 group has no role to play with respect to resonance, but what role it has is that this nitrogen atom is highly electronegative. It can show me minus A effect. It will be an electron withdrawing group, yes, right? But this time not with the help of resonance, but with the help of your inductive effect, right? So now what is more powerful? Definitely resonance is more powerful when compared to inductive effect, right? So even though this is an electron withdrawing group, but at meta position, it is not able to do with resonance. It can do only with your inductive effect. So compared to this molecule is going to be less basic. But compared to this one, that is the first one and third one, if you compare, definitely the negative charge is getting stabilized more because of inductive effect, along with the resonance structures, along with the normal things that are happening, right? So definitely compared to the first one, third one is more basic, whereas compared to the third one, second one is more basic. Again, because there in second one, the stabilization is happening because of resonance. That is minus R is also happening. Minus I also can happen, right? Again, inductive effect also is going to be favorable only because the nitrogen is more electronegative, right? Okay. Now, when you go to the last one, what is happening? When you go to the last one, already the resonance structures, whatever happens for the phenoxidone, that will happen. But along with it, what are you seeing? This is an electron donating group, right? This is an electron donating group. And that electron donating group is now it is going to push the negative charge towards your oxygen atom only, so the negative charge will increase. And more charge increases, stability decreases. Right? So do you understand that?
Sir?
Yeah.
Sir, did you mean acidic or basic?
We are talking about acidic strengths here.
Sir, so it should be more acidic, right?
No. So now what you understand is because of the availability of lone, because of this electron donating group, the negative charge on the oxygen atom is increasing. So what will increase? Then basic strength will increase. Okay, you come to by your point only. Basic strength will increase. But so what will happen to the acidic strength? Decrease.
Yes.
Right? Okay. Or you can speak in terms of stability directly. So remember that charge, the amount of charge and stability are inversely proportional. More and more neutral the molecule is, more and more it is stability. Right? So compared to the amount of negative charge will I have on the phenoxide ion, here the negative charge will definitely be higher because of this. So can I say this is more neutral, so this is more stable, and this is having more charge, so this is less stable.
Sir?
Okay. Yeah.
Sir, so the structure with CH3 is most basic.
Yes, most basic, so least acidic. So if I ask you to arrange them in the order of acidic strength, you will give 4th rank to this, least acidic of them all. Right? Okay. Now this is going to be maximum acidic. Now wherever the negative charge was getting stabilized by resonance, right? That was in the case of your nitrogen this year, ortho, right? So this will get the 1st rank. And here it is getting stabilized, right? But only with inductive effect. So the 2nd rank goes to this, and obviously the 3rd rank goes to normal phenol. Like this, you go for acidic strength. So acidic strength, what is the criteria? You will remove the H+, you make the conjugate base and check for the stability of the conjugate base. But in case of basic strength, what do? You go for availability of lone pair because we're talking about electron donation thing. Right? I hope it makes a lot of sense.
Yes, sir. Got it.
Right? Okay. So I think we have done enough for today. Right? Next class we'll see. Right? A lot of things you learned today. Please keep revising these things, or else you'll forget. Right? Okay. And let's stop this for today. Thank you so much.
Thank you.
Thank you, sir.